Hello students, now we will discuss growth of current in LR circuit. Growth of current in LR circuit. Let a inductor of coefficient of self-induction capital L and a resistor of resistance capital R connected in series across a battery of EMF capital E through a two-way key as shown in the figure. See in the diagram, this is a inductor of coefficient of self-induction capital L and a resistor of resistance capital R connected across a battery of EMF capital E, and this is a two-way key with the terminal 1, 2 and 3. Terminal 3 is connected to the negative terminal of the battery and terminal 1 is connected to the other end of the resistor and other end of the inductor L is connected to the terminal 2 of two-way key. Now initially when the battery is not connected, the current in the circuit is 0. That is, at t is equal to 0, capital I is equal to 0. Now when terminal 1 is connected to terminal 3, see in the diagram, terminal 1 is connected to terminal 3, the current starts increasing. See in the diagram, current starts increasing. At any instant, it is let it be capital I. And with the result, an induced EMF is set up in the inductor which opposes the growth of current in the circuit. If capital I is the current and dI by dt is the rate of increase of current in the circuit at any time t, then induced EMF E, small e, in the inductor is given by small e is equal to minus L into dI by dt. Let it be equation number 1. Negative sign show that the induced EMF opposes the increase in current in the circuit. Therefore, according to Kirchhoff's second law or loop rule, now in the closed circuit, I into capital R, as there is only one resistance, so I into R is equal to capital E minus L into dI by dt, which is total EMF in the circuit. Capital E is EMF of the battery which is applied, and L into dI by dt is the induced EMF in the inductor, and negative sign show that it is opposite to capital E. Let it be equation number 2. When the current in the circuit becomes maximum, the growth of current becomes 0. That is, there is no change in current in the circuit. That is, for I is equal to I naught, that is, for capital I is equal to capital I naught, dI by dt is equal to 0. There is no change in current in the circuit. Therefore, from equation number 2, we get I naught R is equal to capital E minus 0. This implies capital E is equal to I naught R. Putting this in equation number 2, we get I into R is equal to I naught R minus L into dI by dt. That is putting the value of E. Now by rearranging, so we get L into dI by dt is equal to I naught R minus IR. In the right hand side, we can take capital R common. So we get L into dI by dt is equal to I naught minus I into capital R. This is a differential equation, and separating the variable we get 1 upon I naught minus I into di is equal to R upon L into dt, or again by rearranging, integrating the both sides, we get integration of 1 upon I naught minus I with respect to I is equal to integration of R upon L dt with respect to t plus c, where c is constant of integration. Now again by rearranging, we get minus integration of minus 1 upon I naught minus I with respect to I is equal to R upon L integration of dt plus c. R upon L is constant, we can take common, and in the left hand side the numerator becomes minus 1, which is equal to derivative of the denominator. Derivative of I naught constant is 0 and derivative of I is minus 1. So minus 1 is the derivative of denominator. Therefore, minus log to the base e of I naught minus I is equal to R upon L into t plus c, because integration of f dash x upon fx with respect to x is equal to log to the base e of mod of fx. F dash x is derivative of fx. That is, if numerator is the derivative of denominator, then integration is equal to log to the base e of the denominator. Now log I naught minus I to the base e is equal to minus R upon L into t minus c, that is multiplying both sides by minus sign. Let it be equation number 3. Now at t is equal to 0, capital I is equal to 0. Therefore, from equation number 3, log to the base e of I naught minus 0 is equal to minus R upon L into 0 minus c. This implies log to the base e of I naught is equal to minus 0 minus c, or this implies c is equal to minus log to the base e of I naught. Putting this value in equation number 3, so we get log to the base e of I naught minus I is equal to minus R upon L into t minus into minus log capital I naught to the base e. Now minus into minus become plus, so we get, this implies log to the base e of I naught minus I is equal to minus R upon L into t plus log to the base e of I naught, or by rearranging, this implies log to the base e of I naught minus I minus log to the base e of I naught is equal to minus R upon L into t. Now using the formula of log m minus log n is equal to log m upon n. So this implies log to the base e of I naught minus I upon I naught is equal to minus R upon L into t. Now taking antilog both sides, so we get I naught minus I upon I naught is equal to e to the power minus R upon L into t. Now cross multiplying, so we get I naught minus I is equal to I naught into e to the power minus r upon L into t. By rearranging, I naught minus I naught into e to the power minus r upon L into t is equal to capital I, or capital I is equal to I naught into 1 minus e to the power minus r upon L into t, that is taking common I naught. Let it be equation number 4. Equation 4 gives the value of current at any time during the growth of current in LR circuit and show that current grows exponentially with time. As shown in the graph, suppose this is a origin, this is x-axis, this is y-axis. Along x-axis we plot time t, and along y-axis we plot current capital I, and graph is like this. Current grows like this, and this is the maximum value I naught. Also from equation 4 we find that the current attains its maximum value when e to the power minus r upon L into t is equal to 0, and this is possible when t is equal to infinity. That is, in LR circuit the current reaches its maximum value after infinite time, or we can say the current never reaches its peak value. Current never reaches its maximum value, as infinity is not possible. Now time constant. From question number 4, I is equal to I naught into 1 minus e to the power minus r upon L into t. Now according to principle of homogeneity, the dimension on both sides of the above equation must be same. Also, quantities in the power must be dimensionless. So we can say quantity in the power, therefore r upon L into t is equal to dimensionless, or dimensions of r upon L is equal to dimensions of 1 upon t, or you can say dimensions of L upon R is equal to dimensions of time. So dimension of L upon R is same as that of time. So it is equal to m to the power 0, L to the power 0, t to the power 1, dimension of time. Therefore, the term t is equal to L upon R is called time constant. Now when t is equal to L upon R, time constant, then from the above equation, I is equal to I naught into 1 minus e to the power minus r upon L into L upon R. Now r and r cancel each other, and L and L cancel each other. So we get capital I is equal to I naught into 1 minus e to the power minus 1, or we can write I is equal to I naught into 1 minus 1 upon e. Now within the bracket, taking LCM, so we get capital I is equal to I naught into e minus 1 upon e, or capital I is equal to 0.632 into I naught. That is, putting the value of e, we get e minus 1 upon e nearly equal to 0.632. Hence, time constant is defined as the time during which the current grows to 0.632 times its maximum value, or the time during which current grow to 63.2% of its maximum value. So this is the growth of current in a LR circuit and definition of time constant. So thank you very much.